Okay, so in this new video, we will together discuss open a new series and discuss a new topic called reinforcement learning. Okay, so reinforcement learning, although it is a stream of computer science or machine learning, but it's strongly related to economics, right? And this is because that reinforcement learning, the basic problem in that is to try to solve the problem of dynamic or sequential decision making under uncertainty, right? So it's essentially a decision making problem, right? Although we are people are using the machine learning or the computer science approach to solve this problem, but essentially it's a decision problem that is very interesting in the also in the field of economics to be studied, right? Okay, so first let's have a, as we just mentioned, let's have a rough definition for reinforcement learning problem. Okay, so let's call that RL. So reinforcement learning, RL, essentially it tries to solve a problem of dynamic or sequential decision making. Okay, decision making problem under uncertainty, right? And we know that there's an environment for some agent, and this agent is trying to explore this environment and makes the optimal decision under the changing environment or under those uncertainty, right? So using a little diagram to help us to better understand what's going on here, let's suppose this is the agent. Okay, so here we only have one agent, right? So later perhaps we could introduce some more complicated framework including multiple agents, but here for simplicity of the introduction we simply have one agent, right? So and there is an environment. Okay, so the agent is interacting with the environment, right? And that's some difference between the reinforcement learning and or the machine learning, right? So in machine learning, normally we the data either in a supervised or unsupervised learning, the model that we're training, we have this data that is given to this model to be trained, right? So here the agent has to explore the environment and get some feedback from this environment to train this agent itself, right? Okay, so the agent, as we mentioned, agent observes some state and then takes some action, right? So some action at time period t, right? So after taking some action at, the environment gives some reward to the agent, okay, which is RT, okay, and of course the agent needs to observe some state, right, before taking some action at. So the state, we call this state as ST. Okay, so those are the essential parts that we need for a basic reinforcement learning problem. Okay, so to be more specific, let's make some rigorous definitions. So state S, okay. So here this is still a rough definition. Right? Later we'll introduce a very formal definition on those notations. But here we just need to know the meaning of those things. Okay, so state is S, and sometimes the agent doesn't observe the state directly, but instead the agents they observe some observation. Okay, observation O. Okay, it could be a fully could be a full observation or a partial observation, right? Fully observed or partially observed. Okay. And the action we just mentioned, it could be, so the action space could be either discrete or continuous, right? Okay. So those are different types of random variables, right? And the most important thing in reinforcement learning would be policy, right? If we want to have something to be the most important part, it has to be the policy. So the policy is sort of an analog to the strategy that we have in game theory. Okay, so in game theory, we need some strategies defined for each agent to play in some simultaneous move game or some dynamic extensive form game, right? So here we use the word policy to refer to that concept. Okay, so this policy, it could be, and here we could see that has to be the most important part, because the goal or the aim of reinforcement learning would be to study or to learn some optimal policy or this optimal strategy for this agent to act according to that, right? So that would be very important. And the policies could be deterministic or stochastic. Deterministic, okay. So if that's deterministic, then this AT would be simply some function of ST, okay. All right. Okay, so if that's stochastic, okay, then this AT is randomly distributed according to some policy pi, which is some conditional probability given ST, right? Okay, so those are some deterministic or stochastic policies, and sometimes we might have heard of the deep reinforcement learning, right? So in those cases, the parameters here, so we will have some parameters in those policies, okay? So it'll be more complicated than those simple functions or some simple probability distributions. We will have even a neural network or even something even more complicated than that, right? For those policies. So in such cases, so in the deep learning or the deep reinforcement learning, so we will have, or we use some parameters, okay, in the policies for those models, right? So AT in this case could be written as some mu theta. Let's say this model is represented by theta as a parameter, mu theta ST, or AT is distributed according to this pi theta, okay, with some parameters in this model. Okay, so far we'll just need to know those things, okay, but later we'll have a more rigorous definition or more clear examples for that. Okay, good. So that is policy. Okay, something might be also useful would be the trajectory. Okay, sometimes we call this as episode. Okay, so a trajectory tau is a sequence from the initial state S0, some action A0, and then goes to S1, A1, all the way up to some point or some infinite series. Okay. So, and this S0 would be the starting state distribution. Starting state, like sort of the prior distribution, right? Prior probability distribution. Okay. S0, it has a distribution according to this row 0, okay, which is, it should be just some PDF, right? Okay, so good. Now we have the trajectory or the episode. Then, so here we can notice that we need to basically we need to move from the time period 0 to time period 1 and 2, 3, 4, right? So on and so forth. So how do we move from the previous period to the next period? Okay, so here we need something called state transitions. Okay, so state transition. Okay, so here accordingly we have deterministic or stochastic transitions. Okay, so if it is deterministic, okay, so it has to be st plus 1 will be some function of st and at, which is apparently deterministic, right? It could be stochastic. Of course, in this case, st plus 1 will be distributed according to some distribution p, which is a conditional probability given some st and at, right? So which is stochastic. Good. So as we mentioned, the goal of this agent would be to use some optimal policy to act according to that, and then to try to obtain the maximum reward or the maximum return in this case, right? So what are the rewards and the returns? Okay, so the reward would be just the return for one time period. Okay, so let's say RT for this reward would be some function given st, at, and st plus 1. Okay. Sometimes we won't need st plus 1, right? Here we could sometimes in the literature people write this as simply as RT, which is function of st, or if you want to have at, you can also write at inside. Okay, but normally people don't write st plus 1 here. Okay, because st plus 1 will be given by the transitions. Okay, so so that's reward. And what is return? Return would be a combination of all those future rewards. Okay, so for example, if it is a finite horizon and undiscounted return, it will be something like this. Return with some episode tau would be just the summation of those little rewards from 0 all the way to capital T. Okay, so it could be some infinite horizon discounted return. Okay, so it is R tau, it will be the summation to infinity, but here we have a discount factor gamma to the power of t and times RT. Okay, so those are very straightforward, right? So here we have all those essential parts that we can ensemble them up and to try to express or to formulate the core problem in reinforcement learning, right? So the reinforcement learning problem will be, so the goal of RL is to select some policy. Okay, such policy has to maximize the expected return. Okay, so that would be the key problem in reinforcement learning, right? So, and Alternatively, as we mentioned in the beginning, this problem will be equivalent to some problem where we try to solve some sequential or dynamic decision-making problems under some uncertainty, right? So that's why we have the expectation here. Okay, so those would be the equivalent definitions, right? Okay, so the probability of a t-step trajectory, okay, so let's have something specific, okay, so the probability of a t-step trajectory or episode will be p gamma given some pi, okay. So here the probability, we need simply to multiply all those probabilities in the joint probabilities in each time step, right? So, but before that, first we have the initial row here, right? So this is not p. Row 0, S0. Then this is a product. This is not pi. Product from t0 to up to t minus 1, right? Because we have 1 before already, right? So the probability that we need to multiply will be the joint probability of, here we have this p, st plus 1, given st, and at, right? It's too small, at. Okay, and we need to also time the policy, right? So we have the policy and the transition. Then we have the probability of a episode or a trajectory with capital T step, right? Okay, so in this case, what is the expected return? So the expected return. So now we have the probability p, right? So we simply need to take some integral of that. So let's use j to denote that. So it will be an integral regarding to this tau about, so over this tau, and this integral will be for this return, and this will be the probability here, right? Okay, this is distribution for this tau, right? So the return will be r tau, right? And that is just the expectation over tau, which is distributed according to this pi, and the expectation for the expected return, r pi, right? Okay, good. So formally, then we know that we can observe that the optimization problem could be formalized into the follows. So this pi star will be the argmax, okay, for this j function, right, for the expected return, okay, and correspondingly this pi is the optimal policy, right? So as we just mentioned in the definition, here the goal of this reinforcement learning problem would be to find this optimal policy, right? Okay, good. All right, and sometimes in literature we will also see some functions called value functions or the Q functions, right? So what do they mean? Okay, what's the meaning of those terms? Okay, sometimes those will be quite confusing, right? Especially sometimes we have V, capital V, and sometimes we have capital Q, but sometimes we might just be quite confused about those things. Okay, let's see what are the meanings of those things. Okay, so the value function. So those are very important and also very useful concepts, right? So it's really good, helpful for us to have a look and have a good understanding for that before we get deeper into those problems. Okay, so the value functions are just the expected return if we start in some state action pair and then we act to a policy forever on that. Okay, so the definition would be the expected return if we start in some state and action pair, and then we act to a policy forever. Okay, from that. Okay, so that would be a rough definition. Okay. So we have two different kinds of value functions. Okay, so the first kind of that is called on-policy value function. Okay. So it's denoted by this V, okay, and has a superscript of pi, given some say S. Okay, so this S here, okay, notice that this S is essentially a something for the state where we start. Okay, it's not some random state. It's just some state that it's just a starting state. Okay, so it is an expectation over this tau, and for this expected return. Okay, and here we see this, what I mean just a second ago. So here it will be S0 equals to S. Okay, so this S is just the starting state. Okay, nothing like that. Good. And correspondingly, we also have a on-policy action value function. We won't go into off-policy stuff, but here correspondingly we have some action value function, okay, which is more specific than that, given some A here, right? So we also have action value action pair. So we use Q to denote that, okay, to denote this value function, specifically for when we are having this action state pair. Okay, Q of SA, okay, this would be an expectation over this tau. Okay, for this R tau given S0, 0 is S, A0 is A. Okay, so again, this S would be the starting state. Okay, and this A, just some action A at time t. Okay, just some action A at this time 0. Okay, but it might not be some action from policy pi. Okay, might not from pi. Okay, and later we will see more intuitions behind this. Okay. Of course, and correspondingly, we have the optimal value function, which is the maximization over that, right? Okay, so V star, this is from the first on-policy value function, right? So the optimal value function, V star S, will be just the maximization over pi, and the expectation over this tau, and for this R tau given S. Okay, and correspondingly, the optimal action value pair function, action state pair value function, which is in short, we just call this an action value function. Okay, which is denoted as Q star given SA is maximization over this pi and the expectation over tau for this R tau, S naught is S, A naught is A. Okay. Okay, good. And we can notice that after we take the expectation, then we can link those things together. Essentially, we could be just taking another expectation over A and on this Q, right? So we can link those together. They have some relationships. And correspondingly, the stars also have some relationship. V star S is just the maximization over A and Q star, right? good. And the optimal, and also we have some, also sometimes it's also very useful for us to have is a relationship between the optimal Q function and the optimal action. Okay. Q function and optimal action is that the optimal action would be just the argument x of this Q star, right? Okay, good. So in this video, we introduce some very basic fundamental parts that we need in a standard reinforcement learning problem. So in the next video, we'll introduce the Bellman equation and address the importance why we're having this action value function and those notations here. Okay, good.